Here is a syllabus for Theory of Computation, MA 514. So the prerequisite is basic discrete mathematics. Syllabus right now you won't understand these jargons. At least in the first few classes you will understand about alphabets, languages, and grammars. So the main textbook that we will follow is this Hopcroft and Ullman. There are other reference books. So Hopcroft Ullman is this book. So this is old version. So there is a newer version by Hopcroft Motowani Ullman, but I prefer the older version because there are some problems in it which are not present in the newer editions. So if you like, you can use the newer version as reference books also, but I will mainly follow this Hopcroft Ullman. Okay. So what is theory of computation? Now you all have some intuitive notion of computation, right? So theory of computation is all about formalizing this notion. So as a kid, how did you learn, say addition, or even the idea of integers? You started with say 2 mangoes, 3 oranges, and so and whatever. So then it matured into this abstract notion of integers, right? So we'll do something similar with computation itself. So maybe you have some intuitive notion that okay, you can feed some data to a computer. That data can be anything. It can be some number, text, image, audio, video, whatever. And the computer somehow processes this information and gives you some output, right? Now none of this is a mathematical entity, right? So the first step is to formalize the information itself, the input, output, or the intermediate information. So that means we need to encode this information as some kind of mathematical entity. The next thing is to express this computer, this information processing part, as some kind of mathematical entity. Okay. So we will see later that there are two distinct categories. So one is a kind of machine, but a very mathematical machine, and other is some sort of rules, some sort of grammatical rules. So in fact we call that grammar. So these are the two broad categories for this model of computation. So this part. Okay. Now these are all fine, but what is the big picture? So if you look at other branches of mathematics, almost always the final question is a classification problem. So if you look at group theory, the most important question is to classify, say, finite simple groups. If you look at topology, then again, the most important problem is to classify this manifolds or whatever. So theory of computation is similar in that regard. Here we classify the computational problems. Okay. So we have not defined what a computational problem is. Later we'll do that. But you have some intuitive notion, right? A problem that you can give to a computer, say, given some number, decide whether it's a prime or not, or some kind of problem. Okay. And you have done maybe some algorithm codes, some programming codes. Okay. So you have some idea about hardness of problem. Some problems take more time, some problems take less time, some problem takes order n square, some take order n, some take order n log n. So those are some kind of classification, right, of problems into according to their hardness. And by hardness we mean how much resource it takes, right? Now here the picture will be much broader, right? So this model of computation that I mentioned, okay, so each model of computation will have some kind of resource attached to it, and the final goal is to classify problems according to their hardness. So let's first concentrate on this point one. So first 1 or 2 lectures will be on this part only. So information is encoded as some kind of patterns. We also call that string. I mean, we will call that string. And these patterns are constructed out of a fixed finite set of symbols. Okay. And this finite set of symbols that I'm talking about, this set is called an alphabet. Okay. So this can be any non-empty finite set. Okay. So for example, I mean, in modern computers, you probably know all the data are actually encoded as some patterns of zeros and ones. So from henceforth we will use the jargon string. Okay, and the strings are made out of this, say, 2 symbols, 0 and 1. Okay, or you can go slightly high level. So say consider texts or programs, the codes that you write in C or Python or whatever. So they are composed of some characters, right? So each program or text you can see as a sequence of symbols, and the symbols are coming from this set. So this is a finite non-empty set. Okay, so this is our alphabet in this case, and we construct patterns out of it. So that pattern, that string, is our input or output or whatever. So we will use some notational conventions throughout this code. So whenever you see this sigma, this capital sigma, almost always it means an alphabet. Okay, that means this is a non-empty finite set and a set of symbols, right? And this sigma star, this is the set of all strings over this alphabet sigma. So strings over alphabet sigma means a string constructed out of the symbols which are in sigma. So take all such strings. So that set of all strings will be sigma star. And usually we use this A, B, C, D, E, F, this sort of English letters, or 0, 1, 2. So this as symbols. Okay, and we use the last few English letters to denote strings, this U, V, W, X, Y, Z. So these are just notational convention we will use to make life easier. So whenever you see something like this, that this small a is in this capital sigma, so immediately you should interpret this as this sigma as a alphabet, and this small a as a symbol in this alphabet, because this is a set of symbols, right? This capital sigma. And if you see that this X is some element of the sigma star, so as I mentioned before, this sigma star itself is the set of all strings over alphabet sigma. So this X is actually a string. So that means a pattern constructed out of the symbols in sigma. So for formal definitions, we have this. Now, we cannot define symbol in theory of computation. This is a primitive notion. Okay, so in any theory, you have some primitive notion. For example, in geometry, point is a primitive notion. Okay, now once you define point, then maybe you can define lines as some set of points and whatever. But points are points. You cannot define it in terms of anything else. And as I mentioned before, an alphabet is a non-empty finite set of symbols. Okay, so non-empty and finite. So this is very, very important. So this finite. So this is important. So if you keep on inventing new and new symbols, then I mean, there is no point. So you need to fix your symbols first, and out of that symbols you can construct infinitely many strings, infinitely many patterns. So you have all sorts of inputs, but those inputs are constructed out of a finite set of symbols. Okay. So you can choose any non-empty finite set as your alphabet. Here I have taken just an alphabet containing 3 symbols. So this ABC, they don't mean anything else. They are just 3 different symbols, ABC. Okay, so now a string or word is a sequence of finitely many symbols in sigma. Okay, so it's a sequence of finitely many symbols. Okay. So that means you cannot have a pattern, say a continuing up to infinity. So no, continuing up to infinity is not an option for a single string, right? So it should be a finite sequence of symbols, and we also allow the sequence to contain 0 symbols, right? So this will be an empty sequence. So an example for this sigma is all these strings. So you can contain 1, 2, 3, 4, 5 symbols, even 0 symbols. So these are all examples of strings over this alphabet sigma. And as I mentioned before, we also consider string of 0 length, and that we denote by this epsilon. Again, this is a notational convention. We always use this epsilon to denote empty string. Okay, so yeah, this one. So now I really want to emphasize this point that symbols are primitive notion. Now we already saw that we use the 0, 1, 2, etc. for symbols. Now when we use those as symbols, you should not treat them as numbers. They are not numbers. They are just symbols. I could have used some hieroglyphic symbol or whatever. They don't mean anything in itself. So all this 0, 0, 1, 0, 0, 1, 1, these are strings. Okay. So this is one pattern, this is another pattern. So these 2 strings are not equal, right? So they are different strings. And you cannot even ask this question as what is 1 plus 1, because plus is not defined on strings, right? So you should not treat them as numbers or anything else. Symbols are symbols, and the finite sequences that you construct out of it are strings. Okay. So now sometimes we need to interpret this as numbers. So that is in fact the point of using this symbols, because we want to encode numbers as strings. Okay, so it's encoding numbers as strings, not the other way around, that we are expressing strings using numbers. Okay, so yeah, since we want to encode these numbers using strings, so we need to fix some encoding strategy depending on our problem, so that you can define as per your convenience for each individual problem. For example, one way could be interpreting this strings as, say, binary representation of integers, right? So you formally need to actually address this kind of function, so which maps this string to natural numbers. Okay, so you need to map this string to natural numbers, and you define it like this, that fx is an integer and x is actually a binary representation of fx, right, for all x in sigma star. So as a string, the 0, 0 and 0 are different, but say f of 0, 0 will be the integer 0. So f of 0 will be the integer 0. So these are all integers 0, right? So whenever you are trying to interpret this strings as something else, you need to explicitly mention that mapping. Okay. Otherwise, these symbols are just symbols. They are nothing else. Okay. Now we have something called length of string, and that is very simple. It's just the number of symbols in a string. Okay. When you say string, you have some alphabet already defined. So you have some number of symbols in the string, and the number of symbols is the length of the string. So in this example, it's 6. And length of empty string is 0, obviously, because this doesn't contain any symbol, right? Now, if you just take, say, one symbol, so is it a symbol or a string of length 1? Now, we identify a symbol as a string of length 1. So we do not make any distinction about a symbol or string of length 1. Right. So in that sense, this sigma, this alphabet, is also the set of all strings of length 1, right? And so far we are saying strings are finite sequences. So in fact, finite sequence, this term itself we haven't defined properly. So we can take this n-fold Cartesian product of sigma, right? So the elements are n tuples. Okay. Now this n tuple we can identify as this string, as this finite sequence of a1 to an. So we won't use this brackets and commas and all. So we can identify this with this string. So in that sense, for all positive integer n, this sigma to the n, so this will be the set of all strings of length n precisely, right? Now this defines it only for positive n. Now we extend this definition by saying that sigma to the 0 is defined as the set containing empty string, because what we want to have is sigma to the n to be the set of all strings of length n. So length 0 string is the only string, empty string. So sigma to the 0 we define as the set, the singleton set containing just this empty string. Now we define sigma star as a union of all this sigma to the I. So it contains all possible strings of length 0, 1, 2, 3, whatever length. Okay. Now we also sometimes use this notation, this sigma plus. So this is the set of all non-empty strings over sigma. So that means we do not include this epsilon string, this empty string. So this union starts from I equal to 1. Okay. So just for some example, if I have this alphabet containing just these two symbols, what will be sigma square? So it will be all strings of length 2, and there are only 4 such strings. And again, sigma cube will be all strings of length 3. So this is the set containing 8 strings, of course. Similarly, if I take say symbol 0 and 1 and take sigma star, it will contain all strings constructed out of 0 and 1, including the empty string. Okay, and all possible strings. Again, so this 0 and this 0, 0 and 0, 0, 0, these are different strings, right? So if you take just one symbol, alphabet constructed out of this one symbol, and if you take sigma star, then it is again epsilon a, this sort of thing, right? Now notice that the sigma star is infinite. It contains infinitely many strings. Okay, but each string itself is a finite sequence. So each string has a finite length. You cannot have a string of infinite length. Okay, so as I mentioned before, if you have something in mind that this AAA is going on forever, for up to infinity, so this is not a string by your definition. Okay, now string concatenation is very simple. If you have two strings, like say A1 up to AN, B1 up to BM, so all these AIs and BJs are symbols, so their concatenation is just another string which you get by putting them side by side. Okay, so you put this string first and then you put this string after that. So whatever you get, this string of length n plus m, so that is the concatenation of this and this. So in fact, if we express the string as a single symbol, say this is a string x and this is a string y, we write their concatenation as just xy. Okay, so here is an example. Say you have some alphabet containing this letters, they are symbols. So this DOG and HOUSE, so they are strings and their concatenation is just and whatever you get by putting them side by side. Okay. And here also we use this notation x to the n. So this naturally means the concatenation of x n times. Okay, again this only makes sense if n is positive, and we define x to the 0 as this empty string because it means that there is no x at all. So that means to be meaningful, it has to be the length 0 string. So again, here is an example. If this x is AB, then x cube is just AB, AB, AB. Okay. Now prefix, suffix and substring. Again, they are very natural. You can guess the definition from the name itself. So if you have a string which you can break into x and y, break into means it's a concatenation of x and y, so then this x is a prefix of z. Okay, so this x is a prefix of z and this y will be a suffix of z. Okay, now you should notice that for any string x, okay, so x will be a prefix of itself, x will also be a suffix of itself, and the empty string will be a prefix of x, and the empty string will also be a suffix of x. Why? Because x you can write as x concatenated with epsilon, also epsilon concatenated with x, right? Now this concatenation operator, so you can see that this is this concatenation is a binary operator on the set of strings, right? And this epsilon, this empty string, acts as an identity element, as the identity element. Okay, so in that sense it's kind of similar to a group. The crucial difference is that there is no notion of inverts. So this sort of entities are called monoid, but we won't use the term monoid, just for information. So again, example, so if you take this string, what are all the prefixes? Obviously empty string is a prefix, so I can say I can chop it here. I can chop it here so that I can treat this a as a prefix. I can do it here so that this a itself is a prefix, and obviously the whole string itself is a prefix. Similarly, I can, if I chop it here, then this b is a suffix, and obviously this empty string is a suffix, and similarly, you get the idea. So similarly, substring. So substring occurs in the middle of the string, right? So if you can write z as x w y, so then this w will be a substring of z. And again, you can see that this Z is a substring of itself, because I can take X and Y to be empty string. In fact, all the prefixes and suffixes are also substrings, but the converse is obviously not true, right? So again, a trivial example, if you take this string, so you can take this part, and this will be a substring. Now, a language is just a set of strings. So a language over alphabet sigma is a set of strings over alphabet sigma, right? So this is a very formal definition of a mathematical language. We in fact call this formal language, but we won't always use formal language, so we will call this just language. And to differentiate it with the usual meaning of language, we say that natural language versus formal language. So natural languages are like English, Bengali, whatever. So this is what we mean by formal language. So it's just a set of strings. So equivalently, we can say that it's a subset of the sigma star, because sigma star is a set of all strings. So it's just a subset of sigma star. So again, whenever you see this expression, as I said, you should always interpret the sigma as an alphabet. So this is a set of all strings. So whenever you see this L is a subset of sigma star, so you know that this L means a language. Okay, language over alphabet sigma. Now, apart from being a subset, there are no other restrictions. Okay, so it can be empty, it can be non-empty, it can be finite, it can be infinite. Okay, so sigma star itself is infinite. So the empty language is this language, thus this empty set. So here is an example. So you fix any alphabet. Here I have taken this alphabet containing 2 symbols, and you take all the strings whose lengths are less than 5. So how many will be there? So you just calculate. But this will be a finite set, right? So this will be a finite set. On the other hand, if you take all the strings whose length are greater than 5, so that will be an infinite set. So that will be an infinite language over this alphabet sigma, right? And sigma star itself is also a language. It's a subset of itself. So this is also a language. So language can be any subset of strings. Now we have certain operations on language. First of all, since languages are sets, so they are sets of strings, we can have all the set operations on them, right? For example, union and intersection. Okay, and if these languages are over this alphabet sigma, then you can see from the definition that these unions and intersections are also strings over set of strings over sigma. So yeah, they are language over sigma. So again, an example, we take this alphabet containing 2 symbols, and this L1 is I times, B J times, and I is greater than equal to J, and similarly L2 is AI Bj, where I is less than equal to J. So if I take intersection, that means I is both greater than equal to J and less than equal to J, so I should be equal to J. So this intersection is this language. And if I take the union, then obviously there is no restriction on I and J, but still the format should be A to the some I and B to the some J. Okay, so yeah. We can take complement. Again, it comes from sets, but for sets, sometimes it's not clear what the universe is. I mean, you have to have some universe, and you can take the complement with that with respect to that universe. So here the universe is the set of all strings. So if L is a language over sigma, so that means L is a subset of this sigma star. So this is the universe. So we take the complement with respect to this. So again, if we take this alphabet, okay, and if we take L to be all the strings which starts with A, okay, all the strings constructed out of the symbol A and B which starts with A. This X is a string, okay, but this A is this symbol, okay. So what will be the complement of this? All the strings which starts with B, okay, it's this part, but remember this sigma star also contains this empty string, which is obviously not in L because it starts with A. So this will also be part of the complement. Now we have seen concatenation of strings. Now we talk about concatenation of languages. So they are related, but they are different. So you should keep this in mind whenever I say concatenation, or you read concatenation. So concatenation of what? String or language. So here we are talking about concatenation of languages. So if you have two languages over alphabet sigma, then their concatenation is written as just this L1, L2. And L1, L2 is defined as concatenation of strings X and Y, where this X is coming from L1 and this Y is coming from L2. Okay. Now this L1, L2 can be disjoint, they can have some overlap, they can be equal, but whatever they are, this concatenation is always defined, and whatever you get using this, that will be the concatenation of L1 and L2. So here I have taken okay, L1 as just this language. So this looks like an alphabet, but that's okay, right? So this is also a string, this is also a string, and language is just a set of string. It can be a finite set of string, and those strings can be of length 1, so there is no problem at all. So this L1 is this language, and L2 similar is this language. So if I take their concatenation, so I get all possible pairs, where the first part is coming from here and the second part is coming from here. So I get AC, AD, BC, BT. Okay. So again, another example. Now this L1 is infinite language. So this is just epsilon A square, A cube, whatever. This is again epsilon B square, B cube. So now if I take the concatenation, then it will consist of strings of this form, so X and Y. So X will come from here and Y will come from here. So this X here will be something of the format A to the I, and so this will be the X and this will be the Y, okay, and this I and J can be anything, they can be 0 because okay. So once we have this concatenation of languages, as I said, they can be, this L1 and L2 can be equal. So then this L to the I is just concatenation of this language L I times. again, this only makes sense if I is a positive integer. So this is where L to the I is defined recursively. So L to the 1 is L itself. Now we also define L to the 0 as this set. So you remember that when we were defining this sigma star, we defined this sigma to the 0 as also this this thing. So this we also defined as this set containing only the empty string. So we use the same convention here, and L to the I is this, and then L star is again the concatenation of all the LIs. So this is very similar to how we defined this sigma star. And similarly, this L plus is defined as concatenation of all this L to the I, where this I starts from 1 instead of 0. So it starts from 1. Okay. Now, just to see this more directly, see, epsilon will be a part of L star, right? Because L star has L to the 0 as a subset, and L to the 0 has this element empty string. So empty string is always a part of L star. So if you take any non-empty string in L star, non-empty string Z in L star, so this Z will look like some x1, x2 up to some xi, where each of this x1, x2, whatever, this xj, so they are string in L, right? Okay, because how do you get L square? So if you take here, so how do you get L square? So that means you take some x and y, both x and y are coming from L, right? So how do you get L? So then again it's some x, y, z, where x, y, z all are coming from L. So this x, y, they are distinct, but they are coming from L. So here will be a generalization. So in fact this will be so this whole thing will be part of L to the I, right? But then L to the for all I, this L to the I is contained within L star. So a string will be in L star, a non-empty string will be in L star if and only if that string can be broken down into this I many pieces, where each piece belongs to L, right? And this L star has a name, it's called the clean closure of L. Okay. So as I mentioned before, if you take this L to be sigma, again remember that this sigma itself can be a language, right? Sigma is the set of all strings of length 1, right? So sigma is language over sigma. So in that sense, if you take this language, then this definition of L star coincides with the definition of sigma star that we defined earlier. Obviously, this L plus also coincides with the definition of sigma plus that we defined earlier. Okay.